to welcome Senthil back to Princeton, and he will tell us about compressible quantum matter.
All right. So thank you very much, Nati, for inviting me to give this talk. Indeed, the work that I'm going to talk about, a lot of it was made possible by osmosis of various ways of thinking in quantum field theory that we obtained by hanging out with Nati and some of his other quantum field theory friends. It won't exactly be the same kinds of things that the same kinds of reasoning that's used in quantum field theory, but it's certainly informed by it. And you'll see as we go along that that is true. So it's a pleasure for me to give this talk to this audience. So before I get started, I want to know, is there anyone that recognizes this picture? Anyone? All right, so let me tell you. So this is a picture of a Fermi surface. It's the Fermi surface of copper. Metallic copper has a Fermi surface that looks like this. So if you Google for Fermi surface of metals and click on Google Images, you'll see all kinds of wonderful shapes which represent the Fermi surfaces of various metals. So the Fermi surface will play a crucial role throughout my talk. So I thought it'd be nice to show a picture of a real Fermi surface. So the work that I'm talking about is based on one paper that we put out in the summer and a couple of others that we'll eventually write. So, so let me first of all introduce my collaborators. So I've been very privileged to work with a brilliant postdoc at MIT, Dominic Els, who really led this project. And I've learned a tremendous amount by working with Dominic, and hopefully we'll continue to learn more from him. So we also had a very good collaboration with Ryan Thongren on some of the more heavy math-related things. And if I have time, I'll mention some work with a student of mine, Ethan Lake, who's a third-year graduate student at MIT. Okay, so let me start with a little bit of motivation. So the main motivation for the work that I'm going to talk about is an old challenge in condensed matter physics, which is how to describe metals that are not, that defy the standard theory of metals due to Landau, known as Fermi liquid theory. So many of you have probably seen a phase diagram of this sort, this of the copper-based high-temperature superconductors. And so in a range of the phase diagram, there is this regime known as the non-Fermi liquid, which is very well characterized empirically, but is completely mysterious theoretically. Okay, so it's a long-standing problem in the field to try and understand what's going on in this regime, right? The so-called non-Fermi liquid. So I should say right away that I will not expect people in the audience to be at all familiar with any of the previous theoretical work on non-Fermi liquids, except perhaps at the very end, I may comment a little bit on some connections to other models, But what I'm going to do in this talk is to discuss in a very, very general way, in a model independent way, the properties of a certain class of phase of matter, or more precisely, a certain class of infrared fixed points that correspond to either phases or quantum critical points in the phase diagram of matter. So this class that I'm going to talk about will include both Fermi and non-Fermi liquids. So the real reason to think about it so generally is so we can learn something about non-Fermi liquids without trying to make a detailed dynamical model of such a non-Fermi liquid metal. Okay, so let me start with something very general. So let me start with a couple of slides remarking about global symmetry in quantum many-body physics. So if you wish, you can think about a quantum field theory, but for what I'm soon going to start talking about, the theory may not be a continuum quantum field theory, at least not in the UV. So I'll more generally say a global symmetry in quantum many-body physics, meaning systems with many infinite number of degrees of freedom and with some notion of locality and so on and so forth. It could be on a lattice, for instance. So in general, there'll be some UV theory, which depending on the details of the dynamics will go into various kinds of low energy behavior. And low energy behavior will be captured by some IR theory, which typically will be a quantum field theory, but not necessarily always. And this global theory and the UV theory will have some global symmetry group, GUV. And the IR theory will correspondingly have some global symmetry group, GIR. And this global symmetry group, GUV, will be mapped to some elements, some subgroup of this IR symmetry group, GAR. There'll be a map that's determined by the flow of this UV theory to the IR, a map of the global symmetry in the UV to the global symmetry in the IR. So I'll be interested in situations where GUV is an ordinary symmetry, what these days everybody calls a zero form symmetry. And furthermore, in situations in which the global symmetry of the UV theory, GUV, is not spontaneously broken in the infrared. Okay, and in principle, even if GUV is an ordinary zero form symmetry, which is what I'm going to be interested in, the IR symmetry in principle may include higher form symmetries and may not just be restricted to zero form symmetries. Okay. All right. Now, so GIR may be bigger than GUV, right? So the IR theory may well have emergent symmetry that's not present in the UV. And furthermore, GIR itself may have an 't-Hooft anomaly, which will be constrained in some way by the UV theory. So in continuum quantum field theory, one will say that there's an anomaly matching condition that restricts, that tells you something about if the global symmetry group, if UV theory has an anomaly in the realization of its global symmetry GUV, that must be preserved as you flow to the IR. We'll see that we'll need a slight, generalization of that statement, a slight refinement of that statement. So I'll just generally say that any 't-Hooft anomaly theory, right? So the 't-Hooft anomaly means that formally means that if you couple background gauge fields to GIR in the IR theory, then if the theory lives in capital D space-time dimensions, in the presence of the 't-Hooft anomaly, gauge invariance is obtained by extending the gauge field action to one higher dimension with a topological term, with a topological action, that topological action is related to what describes a symmetry-protected topological phase in that higher dimension. So there's this correspondence between a 't-Hooft anomaly in D space-time dimensions and its PT phases, symmetry-protected topological phases in D+1 dimensions. Okay? So that's very general. So what I'm interested in this talk is that I'm going to consider UV systems with the global internal U1 symmetry and with lattice translation symmetries on a D-dimensional lattice. So in condensed matter physics, the global U1 symmetry corresponds to conservation of electric charge. Now, it's common in the high energy physics, in high energy physics, to think of electric charge as something that couples to the electromagnetic gauge field. To think of that as a gauge symmetry. But in the context of condensed matter physics, it's usually an extraordinarily good approximation to think of electric charge conservation as a global U1 symmetry, and that's what we'll do throughout this talk. And I'll not specify the Hamiltonian at all, other than to require that it is local. That is, it's a sum of operators that each act on local regions of space, and that the Hamiltonian is consistent with this global symmetry. So this setting includes almost all the models of interest in standard discussions of strongly interacting electrons. For instance, the Hubbard model and various variants of the Hubbard model. But it doesn't include everything that's been discussed in this context. In particular, many of you are probably familiar with the large body of work in recent years on SYK models, which do not have typically the kinds of models that people typically study, do not have translation symmetries, even though they're lattice models. But, so I won't have much to say about SYK models throughout this talk, except perhaps at the very end, I might make a brief comment. So I'm going to be interested in models with lattice translation symmetry, okay? And a lot of the discussion in condensed matter physics is actually about precisely such models. Okay. So my title had compressible quantum matter, so let me define what that means. So let N, which is the electric charge, be the generator of the global U1 symmetry, and let mu be the corresponding chemical potential, the variable that's thermodynamically conjugate to the total particle number. So for our purposes, we'll just define, and this is standard in the condensed matter literature, define the compressibility to be the derivative of the electric charge with respect to the chemical potential. So this is a thermodynamic susceptibility associated with this global U1 symmetry. So compressible phase means a phase of matter where kappa is non-zero. So those are the kinds of phases I'm specifically going to be interested in. So within such a phase, the charge density can be tuned continuously. As you change some microscopic parameters at fixed chemical potential, the charge density will change. And since this derivative is non-zero, yet generically you expect that you can tune the charge density. So the classic example of a compressible phase of matter familiar from undergraduate physics is a free Fermi gas at non-zero density. So it's an elementary calculation in a free Fermi gas to calculate the derivative of the particle number with respect to the chemical potential. Okay, and it's some non-zero constant that you can very easily evaluate. So the non-Fermi liquid metals that we eventually wish to understand are all compressible phase of matter, as far as we know. So that's the reason for being interested in compressible quantum matter.
In this definition, you're considering zero temperature?
Yeah, I'm considering zero temperature. Throughout the talk, I'll only be talking about zero temperature. Thank you. So with the specified global symmetries, global U1 and lattice translation symmetries, we can define an important quantity called the lattice filling, which is the average charge per unit cell. So if you have a lattice like this, so here I'm showing a 2D square lattice, and these blue circles represent particles. So you'll have some number of particles on the lattice. So what the filling is, the one way to define the filling is to take the total number of particles and divide by the total number of lattice sites in the thermodynamic limit, right? So the limit of the number of particles divided by number of, strictly speaking, number of unit cells. So on a square lattice, it's basically the same thing. In the limit that the both the numerator and denominator go to infinity. Okay. So in a compressible phase, we can tune this lattice filling nu continuously, okay, without encountering phase transitions. Okay. So now that was the specification of the UV theory. So that's all I'm going to say about the UV theory. So that's the sort of general setting that we're going to be interested in. Now let's talk a little bit about the IR theory. So the first question is how are lattice translations implemented in the IR theory? Okay?
Sorry, I have a question at this point on the lattice. So
yeah.
do we assume the U1 symmetry acts on site, or you can mix different sites of degrees of freedom?
Oh, I'm assuming that that's on site.
Okay, okay, thank you.
Yeah. So in all the models that are of interest in trying to understand non-formal liquid physics in ordinary solids, it's appropriate to take the global U1 to be an on-site symmetry. I mean, if you want something concrete, think about a Hubbard model or something. Okay.
So then in the IR, there will be no pure anomaly for that U1 itself, right?
That's correct. That's absolutely correct.
Okay, thank you.
Yeah. So a unit lattice translation in the UV theory will go into an infinitesimal translation in the IR theory, right? The IR theory is some coarse-grained version of the UV theory, and the lattice spacing, a translation by a single lattice site in the UV theory will map, roughly speaking, it will map to some infinitesimal translation in the IR theory. But more generally, more precisely, we should allow for action by an internal symmetry of the IR theory. Okay, so a nice example that illustrates this is an Ising antiferromagnet. You can either think about a classical or quantum magnet, it doesn't matter. So let's take a square lattice and you have spins that try to order antiferromagnetically. And imagine that you tune some parameter and tune this to a critical point. For instance, at finite temperature, you tune to the critical point. Now, when you tune to criticality, the IR theory is described by a continuum phi to the 4 theory, where phi is the order parameter of the Ising antiferromagnet. Now, unit lattice translations in the UV take this the antiferromagnetic order parameter to minus of itself. So unit lattice translation is implemented in the IR theory through the transformation phi goes to minus phi, which is an internal symmetry of the continuum phi to the 4 theory, right? So unit lattice translations in the UV theory are implemented as the combination of an internal symmetry of the IR theory times some infinitesimal trivial translation. So this is something that I'm going to assume throughout the talk, that what in the UV is lattice translation will be implemented in the IR as an internal symmetry. And it's generally true for almost all phases of matter. But there are some exceptions to this, which occur if the IR does not involve spatial coarse graining. So, there are some weird examples that are clearly known, and some that have been discussed. For instance, baby versions of the kinds of fraction phases that Nati has been working on, Nati has been discussing in field theoretic terms. There are baby versions of those phases which do not have a spatial continuum limit and do not have continuum translation invariance in the IR. But since this assumption is basically satisfied by almost all phases of matter, I'm going to set the subtlety aside as something to worry about in the future and not worry about in the rest of the talk. And I'll just go ahead and make this assumption. Okay. All right. So let me, to set the stage for the kinds of constraints from the UV on the IR theory, let me start with a very simple example, hopefully familiar to everyone who's listening. Suppose we seek an IR theory that is fully gapped and is trivial, meaning no topological order of any kind. And remember that I declared right at the outset that I'm interested in IR theories where the UV symmetry of global U1 and lattice translation is fully preserved and it's not spontaneously broken. So then if the IR theories are trivial, as I declared here, so that's what is called a band insulator in condensed matter physics. So this is only possible if the UV theory has a lattice filling mu, which is an integer. I'm not counting electron spins. We can think about models without of spinless electrons if one wishes. Right? So this is the familiar statement that familiar perhaps from an undergraduate solid state class, that band insulators require integer number of electrons per flavor. If you include spin, the standard statement is that you need even number of electrons per unit cell. And without spin, the corresponding statement is that band insulators are only possible if mu is an integer. Okay. Now,
Could you have a situation where you have a symmetry breaking that makes the effective lattice bigger?
Yeah, you can certainly have that. Yeah.
What?
You can certainly have that.
But then wouldn't that not have an integer lattice filling?
Yeah. So that's why I declared at the outset that I'm only going to be talking about situations where the GUV is unbroken spontaneously in the IR.
Okay, thank you.
Sure. So there are more complex and more, interesting examples of the kinds of constraints that we'll soon talk about, constraints from the UV on the IR theory. So the flavor of all these constraints is that they are model independent. They don't depend on knowing any particular Hamiltonian. So there are two famous theorems in condensed matter physics. One known as the Lieb-Schultz-Mattes Oshikawa-Hastings theorem. And the statement of this theorem is that if mu is a rational number, like P over Q, then ground states that preserve GUV must either have topological order or be gapless. Okay? So that's the first theorem. And the second theorem is another famous theorem due to Lutringer. It's a statement about Fermi liquids. And the statement is that the volume of the Fermi surface is fixed by electron filling in pretty much the same way as in a free fermion problem. Namely, the Fermi volume divided by 2 pi to the d is equal to nu mod z. Okay. Here I've set things like the lattice constant to be equal to 1. Okay, and the mod z. So for free electrons, for free Fermi gas, we don't have this restriction that it's only mod z. Rather, it's just the full statement. On a lattice, the mod z takes into account filled bands that are completely occupied. Okay. Anyway, so this Lutringer's theorem is due to Lutringer, who gave a perturbative proof. He proved it to all orders of perturbation theory, starting from the free Fermi gas in the 1960s. And there was a non-perturbative argument given for the same statement much later by Masaki Yoshikawa in 2000. And this is a wonderful example of the kind of constraint that I'm going to talk about in the rest of this talk. Okay, so here's a rough plan for the talk. I'm going to think about UV systems with GUV being U1 cross translation. And the IR, I'm going to assume that these symmetries are unbroken and that the ground state is compressible. That is, nu can be continuously tuned. Okay? So what we'll see is that there are strong constraints which generalize Lutringer's theorem on the structure of the IR theory. Okay? So we'll make no assumption that we will not need to assume that the ground state is a Fermi liquid or is doing something else. So these are the only assumptions, right? And these constraints must be satisfied by any IR model that one wants to write down that is emergible in the sense that it is capable of emerging from the UV theory with these symmetries and with these assumptions, right? So along the way, we'll obtain a new non-perturbative proof of Lutinger's theorem, okay? So that's the general plan. So here's a more detailed plan. I'll start with systems in one spatial dimension. So I had somewhere I'd indicated what little d and capital D. So little d will always be the spatial dimension and capital D will be the space-time dimension, right? So I'm going to start with systems in one spatial dimension and show that the familiar chiral anomaly in 1+1 dimensions directly implies Lutinger's theorem. Next, I'll go to two spatial dimensions and talk about the example of Fermi liquids, which I'll discuss from a modern perspective. I'll revisit the theory of Fermi liquids, and we'll see that the Fermi liquid has an emergent IR symmetry, which is a very large symmetry. It's what's known as a loop group. And we'll see that the anomaly of the emergent symmetry of the Fermi liquid is correctly captured by a 5-dimensional Chern-Simons action, even though the theory lives in 2 space dimensions. And then we'll see that the Lutinger's theorem that follows directly from the anomaly that's captured by this 5D Chern-Simons action. And then I will talk about a general theorem for incompressible, sorry, I have typos left, for compressible phases in D bigger than 1. And this will give us a conjecture on a wide class of non-Fermi liquids, probably all non-Fermi liquids with these symmetries, which we'll call Sard's Fermi liquids. And that's probably all that I'll have time to talk about. But if there is further time, I'll talk about an application to experiments from this understanding. And it's always complicated to apply theory to experiments and complicated many body condensed matter systems. But one advantage of what we've been trying to do here is that we're not trying to answer hard dynamical questions. And what we are doing is very, very general, based just on a few assumptions. And so we can hope that anything we have to say about experiments has less chance of being incorrect. But of course, it also has less chance of being a detailed theory, right? But amazingly enough, it turns out that we'll be able to make a concrete prediction for experiments based on these very general considerations. Okay, so let me start with the chiral anomaly and Lutinger's theorem. So I'm going to talk about fermions at finite density in one spatial dimension. And let's start with free fermions at non-zero density in 1D. They'll have some dispersion, epsilon k. And at finite density, you'll fill up a Fermi C up to some chemical potential mu. And that will then define Fermi momenta kf and minus kf. Now the IR theory, the IR description of the system is obtained by linearizing the dispersion near each of the 2 Fermi momenta. And as it's well known, the IR theory is a massless Dirac fermion. And this IR theory has a global symmetry of U1 cross U1, corresponding to separate conservation of these right-moving and left-moving fermions. Now, if we add interactions to the theory, short-ranged interactions, the interactions are a marginal perturbation and they lead to a fixed line. In the condensed matter literature, the theory on this fixed line is what's known as a Luttinger liquid. And this Luttinger liquid preserves this global U1 cross U1 symmetry that was already present in the free Fermi gas, right? In the IR theory of the free Fermi gas, okay? Now, we can ask how the UV symmetry of the theory is embedded into the IR U1 cross U1 symmetry. And for simplicity, throughout this 1D discussion, I'm going to assume that the translation symmetry is a continuous translation symmetry in the UV. And it's easy to extend the argument if the UV theory is a lattice theory. So the UV, instead of talking about we can just talk about the generators of the global U1 and translation. And so there'll be some total charge Q and some total momentum P. And these, in the IR theory, they correspond to simple objects in terms of the generators of the left moving and right moving U1s. The total charge is simply related to n left plus n right, while the total momentum is the Fermi momentum times n right minus n left. Okay, so these equations provide the embedding of GUV into the U1 cross U1 symmetry of GIR. Now, if you just think about the IR theory, the global U1 cross U1 symmetry, it's well known that it's broken by external gauge fields. For instance, if I turn on an external electric field that couples the total charge, there's the well-known chiral anomaly. It's an example of an 't Hooft anomaly, where the separate conservation of the left and right moving currents is violated by terms that are proportional to the external field strength. Okay. So we can understand this by thinking about the original model with the full dispersion and so on, but we'll just take it as a property of the IR field theory, whichever way one wants to understand. So now let's see how this chiral anomaly, these anomaly equations immediately lead to Lutinger's theorem. So in the original UV theory, if we turn on an electric field, from Newton's law, we know that the total rate of change of momentum is the total electric charge times the electric field. Okay, so dp dt is n times E. Now in the IR theory, from the anomaly, we know that dp dt is kf times the time derivative of n right minus nl. And we use the anomaly equation to, in the previous slide, and integrate over all space to get the result that this derivative is equal to kf times E times L over pi, where L is the length of the system. So comparing these two equations gives us a relationship between kf and the total particle electric charge. So it tells us that kf is pi times the density, which is exactly the statement of Lutinger's theorem. Okay. So this is an old argument, and it's well known in the Currents matter in Currents matter physics. I'm not sure who exactly was the first person to discuss this, but it's sort of understood by many people working in this field. Okay. So this gives us the first hint that perhaps we should try to understand Lutinger's theorem in terms that, using language that involves concepts like anomaly and anomaly matching and things of that sort. Okay, and that will then be a non-perturbative way to think about Lutinger's theorem. Okay. So any questions on the 1D story? No? Okay, so let me go to 2 dimensions and talk about Fermi liquids. So I'm going to specifically talk about the famous Landau Fermi liquid in 2 dimensions. So the UV theory to be general, I'll take it to have a global symmetry, which is the charge U1 times lattice translations. For instance, think about a square lattice. So then lattice translations will correspond to the group Z squared. And the IR theory, according to Landau, has well-defined quasi-particles near a sharp Fermi surface. So the surface in momentum space, and all the low energy excitations live near the surface, and and they're described in terms of quasi-particles with some dispersion near the surface. So according to Landau, the IR Hamiltonian can be written in terms of the quasi-particle number at point K near the Fermi surface. So here the sums over K's are restricted to K's near the Fermi surface. And so there's two terms that Landau argued you need to keep. The first is just corresponds to a dispersion of the quasi-particles. The second corresponds to forward scattering interactions between the quasi-particles, which does not change the quasi-particle number, but changes the energy of a quasi-particle state when other quasi-particle states are excited. Okay. So this essentially all that I'll need from Fermi liquid theory. So the question that I want to address right away is, what is the emergent symmetry of the Fermi liquid? Now, the colloquial statement about this emergent symmetry is that the quasi-particles are separately conserved for each point of the Fermi surface. So let's make this colloquial statement into a sort of more precise statement. Okay? For each point on the Fermi surface, there's a conserved charge density n theta, right? Where n theta d theta is the number of quasi-particles between theta and theta plus d theta, where theta is a parameter that labels points on the Fermi surface. It doesn't exactly have to be the angle, but it's some parameter. The Fermi surface is, in the simplest example, it's topologically the same as a circle. So we can label it by some coordinate theta that labels points on this curve. So general IR symmetry element is given by e to the I integral d theta f of theta and theta for smooth functions f of theta. Okay, so these define smooth maps from a circle to U1, which form a group known as the loop group. And I don't know if this symbol is standard. Collaborator Dominic proposed to use this symbol. Maybe it's standard, but we'll call it LU1. And the definition of LU1 is precisely that it defines, that it describes smooth maps from a circle to U1. So we'll identify this as the infrared emergent IR symmetry of the Fermi liquid. It's this loop group. Okay. So let's ask how the microscopic symmetries, the GUV, embeds into this GIR. So the total charge n is the integral d theta of n theta. That's just the total number of quasi-particles near the Fermi surface, right? Now, so this statement is reasonably obvious. More interesting are unit translations along either the x or y direction on the lattice, right? Setting lattice constants to be 1. So T alpha, unit translation in the alpha direction, is e to the minus I integral d theta kf alpha times n theta, right? So if you translate by an amount, by 1 unit, along say the x direction, then the quasi-particle at point theta of the Fermi surface will acquire a phase which is e to the minus I kf times kf alpha at that point theta. So naturally, therefore, T alpha acts on the full set of quasi-particles in this way. So this will give you the correct phase factor for the action of translation for each point on the Fermi surface. Okay, so both U1 and lattice translations of UV map to elements of the emergent LU1 IR symmetry. In fact, it's interesting, and it's the right thing to do, is to take the action of translations in the IR theory to be the definition of the Fermi momentum in the IR theory, right? So, in a Fermi liquid, we have many ways.
Could I ask a question? So this symmetry is not spontaneously broken, if I understand correctly?
Yes.
Okay. And are you going to have LU1 or LU1 times LU1?
I'm just going to have LU1.
Okay.
Okay.
I have a more elementary question.
Yeah.
There seem to be, in fact, I could have asked this question already in the 1+1 dimensional example.
Mm-hmm.
There seem to be two notions of momenta here.
Yes.
One is the momentum of the axis translation in the infrared, and the other is the J left minus J right that you had. Left minus. There must be some interesting interplay between the underlying translation of the lattice and these two different notions of translations at long distances.
Yeah, so that's what I said in some earlier slide. The unit lattice translation on in the UV maps to an internal symmetry times an infinitesimal translation of the IR theory. Right. So if you wish, there are additional terms in the identification of the momentum which involve the momentum of the IR theory. But the leading term in the momentum just comes from J right minus J left.
So in the previous example, when you discussed 5 to the 4th, this was a Z2 symmetry, so there was no way to be confused. But here you suddenly have two continuous symmetries. So I'm surprised that they're not mixed at lower order.
Oh, they will mix. Yeah, so of course, if I have a lattice in any of these examples, it's still a discrete symmetry in the UV, right? So, so the question arises, if you don't have a lattice in the UV, right? If you just have translations in the UV, continuous translations in the UV, it will mix with the continuum momentum of the IR continuum theory. But it'll also have an additional piece, which is an internal symmetry operation.
Okay, thank you.
Sure.
Excuse me.
Yeah.
Can I ask something about the global symmetry analysis on the Fermi surface?
Yeah.
Is that true? Is that you have some assumption that rule out the case that if you have a gauge fields talking to different side of Fermi surface, I think the analysis for the symmetry may be different. So do you have some assumption for not consider those cases?
Oh, right now I'm only talking about a Fermi liquid. This is still an example.
Okay.
Yeah.
No,
so the Fermi liquid, we know how the symmetry acts. Right? So there's no gauge fields or anything.
Not in this talk. Or will this will be discussed somehow?
I won't discuss it in this talk.
Okay.
Then we've discussed it in the paper that we wrote, but I won't have time to discuss this in the talk.
Thank you.
Sure. So it's fruitful to take the point of view that will define the Fermi momentum by specifying the action of translations in the IR theory. Okay. All right. So we understand the emergent IR symmetry of the Fermi liquid. Now let's ask about the anomaly, the possible tooth anomaly of this theory. So there's a simple physical manifestation. So let me first discuss the physics of the tooth anomaly, and then I'll discuss it in formal terms. So if we turn on an external electromagnetic field, just like in the 1D example, in the 1+1D example, in the two-dimensional Fermi liquid as well, the separate conservation of n theta is destroyed. For instance, if you turn on an electric field, the entire Fermi surface will displace to the right, and all the particles will accelerate. So say that story is very similar to the 1+1D example. That will destroy the conservation of separate conservation of n thetas, and only the total charge will be conserved. And a different example, instead of an electric field, we can consider an external uniform magnetic field. And a uniform magnetic field will lead to a V cross B Lorentz force on the electrons. And this leads, even in the lattice and a Fermi surface, even in the Fermi surface that develops in the lattice system, there's a semi-classical description of electron dynamics on the Fermi surface, which leads to equations very similar to the familiar Lorentz force law. And the rate of change of the quasi-particle momentum is given by the quasi-particle velocity cross product with the external magnetic field. So the quasi-particle moves around the Fermi surface, right? Which means that the separate conservation of n thetas is once again spoiled, even in the presence of a magnetic field. So it's clear that there will be an anomaly, right? So the symmetry of separate conservation of n thetas is only present so long as we do not couple in this external electromagnetic fields, and the coupling in to this external fields breaks that symmetry. So let's just study this formally by coupling in background gauge fields and seeing what happens. So the tooth anomaly is signaled by the breakdown of gauge invariance in the theory, which is cured if we extend the gauge fields to one higher dimension with a topological action, right? Now, for our case, where the IR symmetry group is the loop group LU1, then the gauge field, the appropriate gauge field, is something that has 4 components, A0, AX, AY, and A theta, which are all functions of T, X, Y, and theta. Okay? So in other words, we have to include the theta coordinate as elevated to the same status as time and the 2 space coordinates. So what we really have is a 4-dimensional U1 gauge field, and that corresponds to a gauge field that couples to this loop group symmetry LU1. Now there's a very nice interpretation of A theta, which corresponds to things that are familiar in the standard Fermi liquid theory in Greenwich matter physics. So A theta is a gauge connection in theta space, and theta labels points on the Fermi surface. So the gauge connection that enables you to connect 2 different points on the Fermi surface is precisely what's known as a Berry connection on the Fermi surface. So we see that to properly couple background gauge fields to the IR symmetry, not only do we need the external electromagnetic field, we also need the Berry connection. Okay, so there'll be a 4-dimensional U1 gauge field that couples the system. So naturally, any anomaly related to that will be related to a 5D topological action for this U1 gauge field. Okay. So the corresponding action, not surprisingly, is just 5D Chern-Simons theory, the standard Chern-Simons action, with the coefficient that is quantized in units of 1/24 pi squared. And the claim is that this 5D Chern-Simons theory with m equals ±1 correctly captures the physics of the anomaly of the emergent symmetry of the Fermi liquid. Okay. Okay. So it's actually interesting because we start with a theory that lives in 2 space dimension and is 1 time, right? And but So naively, one might have thought that any anomaly in this theory will correspond to a 3+1 dimensional SPT phase, 3+1 dimensional topological action. But instead, we've ended up with a 5-dimensional action given by this Chern-Simons theorem. So how should we think about the emergence of this extra dimension? So it's a useful physical picture. It's this picture that I'm providing in this slide is strictly speaking not essential for anything, but it sort of gives, at least it gave me, some reassurance that there's some actual physics in this extension to 5 dimensions.
Senthil, I have another question.
Yeah.
To define a Berry connection, you use a projection to some low energy set of states.
Right.
But for that projection to be well defined, you need to have some kind of gap over the parameter space where you're, in this case, your theta. But you're talking about a Fermi surface, so there's no gap. So it's not clear to me that the Berry connection is really well defined.
Oh, so in free fermion theory, let me maybe explain it first in free fermion theory. So we have a set of bands.
And it perfectly well in an insulator, but you're talking about a Fermi surface.
Yeah, no, sure. So let's talk about a metal with a Fermi surface, but let's first talk about the free fermion theory, right? The free fermion theory, there'll be a set of bands, and each band will have a set of block vectors that describe the wave function at each k point. Now, from those block vectors, I can define a Berry connection, right? And that Berry connection will be defined through the below zone.
You're saying that there's a gap for fixed k.
Exactly. That's right. That's exactly what I'm saying. Yeah. So given that Berry connection, there'll be a Berry curvature, and that is well defined through the below zone. And then if I occupy states within some Fermi surface, there is a Fermi surface Berry connection which is actually important data in specifying the low energy theory of the Fermi liquid. It was famously argued by Haldane about 14, 15 years back that this leads to a measurable effect known as an anomalous Hall effect in a Fermi liquid, which people had discussed in the 1950s, but the interpretation in terms of this Fermi surface Berry phase came only in 2007 or something, maybe 2006. Okay, so this useful but unnecessary physical picture is that we simply interpret the 5th dimension as going into the interior of the Fermi surface, right? So our theory lives on the Fermi surface, but if we wish, we can think about an extension where we define the theory in the interior of the Fermi surface. So then we can think about this 5D U1 gauge field as living in 2 space and 1 time and 2 momentum directions. After all, theta is a momentum direction. So the interior of going into the interior of the Fermi surface is another momentum direction. And so that then gives us the total of 5 dimensions, right? And the Fermi surface is the boundary of the rigidly occupied Fermi C. So we can think of the Fermi surface with its x, y, and theta and t and time directions as simply defining the boundary of the Fermi C, which of course is the standard point of view. Okay. Now let's talk about the manifestation of the anomaly. So we turn on 2 pi flux of the electromagnetic gauge field, AX and AY alone, and let's turn on a uniform 2 pi magnetic flux. Now it's easy to evaluate this 5D Chern-Simons action in the presence of such a 2 pi flux for AX and AY. And it's easy to see that it reduces to a 3D Chern-Simons term for the remaining 3 components. Okay, and furthermore, as a consequence of this 3D Chern-Simons term for the remaining three components, for the boundary theory at the Fermi surface, the n theta, these quasi-particle occupations in theta, they satisfy the Kac-Moody algebra familiar from the theory of a 1D chiral fermion. So earlier, in the absence of this magnetic field, these n thetas all commute with each other. But now, in the presence of this magnetic field, these n thetas stop commuting with each other. And furthermore, the commutation relation is precisely that of the densities of a 1D chiral fermion. Now, this, of course, ties in very nicely with the expectation that the quasi-particle moves chirally around the Fermi surface in a magnetic field that comes from familiar semi-classical considerations, right? So if I go to this equation, if I turn on a magnetic field, the quasi-particle moves around in one direction in momentum space around the Fermi surface. Okay, now, so just from that, one might have guessed that there'll be a 1D chiral fermion at the Fermi surface in a magnetic field. But this formal story that I told you correctly reproduces that expectation, but also makes it more precise. Now, there's an interesting point of view. Again, it's not necessary to take this point of view, but I found it interesting to take this point of view. So when we turn on this 2π flux of the electromagnetic field, this 5D Chern-Simons term, as I just said, reduces to the 3D Chern-Simons term for the remaining three components. Now, the remaining three components are what? So I've already used AX and AY. The remaining three components are the time direction, the theta direction, and this extra fifth direction, which, as I said, if one wishes, one can think of as going into the interior of the Fermi surface. Okay, so this means that this 3D Chern-Simons term can be thought of as describing an integer quantum Hall effect in momentum space in the interior of the Fermi surface. Okay, so we think in the presence of a 2π flux, the statement then is that you can think of the rigid interior of the Fermi surface as harboring a quantum Hall state in momentum space. And the Fermi surface is the boundary in momentum space of the Fermi C, right? And so naturally, if the Fermi C has become a quantum Hall state, then the Fermi surface itself will have a chiral fermion, okay? So that's a point of view. Perhaps some of you find it interesting and useful. I certainly found it interesting and useful. But we don't need that point of view. All right, so next let me argue how Lutinger's theorem follows directly from this anomaly. Okay, so let's go back to the UV theory, and the chain of reasoning is going to be very similar to what I described in 1+1D, but now on lattice in 2D. On the UV theory, in the presence of 2π flux, the discrete unit translations do not commute. And the lack of commutation is expressed by this equation, Tx, Ty, Tx inverse, Ty inverse, is e to the 2π I nu, where nu is the lattice filling. It's the average number of particles per unit cell. So a heuristic way to think about this statement is simply that rather than moving the particles, we can try to move the flux while keeping the particles fixed. So if I move a 2π flux around the lattice site, right? If I have 2π flux here and I move it around and the average charge is nu, then it picks up an Arnaud-Bohm phase, which is precisely 2π times nu. Okay? So for this reason, even though in the absence of magnetic flux, discrete unit translations commute, in the presence of magnetic flux, they fail to commute. The lack of commutation is given precisely by the lattice filling nu. Next, we want to calculate the same quantity in the IR theory by using the known identification of T alpha in terms of these loop group operations, right? So doing this calculation is very simple because in the presence of 2 pi flux, we also know the commutation algebra of n thetas, and it's this Kac-Moody algebra, right? So then we just plug it in and do the calculation, and we find that this object, tx ty, tx inverse, ty inverse, is precisely given by e to the I times the Fermi volume divided by 2 pi. Ax and ay lattice constants, which had said equal to 1, but apparently forgot about it and reinstated them here. So then we need to match these two things, and matching them exactly gives us Lutinger's theorem. Okay, so this is a non-perturbative view of Lutinger's theorem, which makes it clear that it comes from the anomaly of the emergent IR symmetry group. Okay, and also gives us so all of this discussion further supports this claim. Oops, lost my, what did I do? Excuse me. I should find my talk. Sorry about that. I seem to have lost the talk. I'm trying to get Keynote to start up again. All right, I think I'm back in action. Okay, so that's the statement about Lutinger's theorem and the anomaly. So a general comment is that apart from Lutinger's theorem, many other universal properties of the Fermi liquid follow just from knowing its emergent symmetry and its anomaly. Many, but not all, universal properties. For instance, the response to electric fields, the response to magnetic fields is a phenomenon known as the de Haas-Van Alphen effect, which is extremely useful in determining the shape of the Fermi surface. These collectively are known as quorum oscillations. So phenomena like these are universally determined in terms of the emergent symmetry and its anomaly. And these are what we call the kinematic properties of the theory. And they must be distinguished from dynamical properties that require knowledge of details of the IR Hamiltonian, for instance, the Fermi velocity or things like that. Right? But these kinematic properties, which follow generally from the emergent symmetry and its anomaly, do not require knowledge of the detailed Hamiltonian. So those were two examples, and one in 1D and the 1 plus 1D and the 2D Fermi liquid. So the last few minutes, let me talk about more general compressible phases. The main result in this direction is a theorem that for any irrational filling nu in D bigger than 1, a spatial dimension bigger than 1, with GUV being U1 times lattice translations, that GAR cannot be a compact Lie group. Okay. Now we can only prove this so long as we assume that GAR only includes zero form symmetries, but on physical grounds, it seems likely that it holds even with higher form symmetries. So let me give you a sketch of the line of reasoning that leads to this theorem. It turns out the theorem is actually simpler to understand. You know, the rationale for the theorem is simplest to understand in two space dimensions. Now, in any dimension, and the general idea is that in IR theory, we relate the filling mu to an anomaly of the emergent IR symmetry, just like what happened in the 1 + 1D example and in the 2D Fermi liquid. And because it's related to an anomaly of JAR, it's determined by a topological action for an SPT phase protected by JAR in D + 1 dimensions. Now, for D + 1 = 3, that is for D = 2, so we are in spatial dimension D + 1 = 3. SPT phases with compact Lie groups so such that Q copies are always trivial for some finite integer Q. So I learned from my collaborators that this is what's called, people say that the corresponding group that classifies these SPT phases are fully torsion. I didn't know that word before. This means that the anomaly of the boundary theory is trivial for Q copies of the theory. And so mu must be equal to P over Q with P an integer. Okay, so this is almost a trivial statement if one knew this statement that in 3 space dimensions, SPTs with compact Lie groups are such that Q copies are trivial. Now it turns out the statement is also true and can be proven when D + 1 is 4 or higher dimension. At least for zero form symmetries. So Fermi liquids satisfy this as LU1 is infinite dimension. Okay, so which then raises the general question of what can happen beyond Fermi liquids. Okay. So what is the emergent internal symmetry of a non-Fermi liquid metal with these symmetries, with these UV symmetries, which is such that these symmetries are not broken in the IR? So there's 2 possibilities that one can think of. The first is that it's sort of like the Fermi liquid in that it has infinite dimensional emergent symmetry. Maybe it's exactly the same as the Fermi liquid LU1 or it's some variant thereof. So this is what we call an ersatz Fermi liquid. And these ersatz Fermi liquids will have many, many properties that are very similar to Fermi liquids, even if their detailed dynamics is completely different. You know, they're non-Fermi liquids. So there are many examples of this type of non-Fermi liquid. For instance, there's a model that's very popular in the chemistry matter literature of a Fermi surface coupled to a critical boson. And there's a standard treatment of this model, initiated in fact by Joe Polchinski and a lot of subsequent work. Within that theory, there's again an infinite dimensional emergent symmetry. And so that's one possibility. Now, logically, there's another possibility, which is that the emergent symmetry is a finite dimensional group, but it's a non-compact Lie group. So this, we do not know if this is a legal possibility or not. It feels like something that one may worry is somehow illegal, but I don't know. I personally do not know if it's illegal. My collaborator, Dominic, suspects that there's something bad about this possibility as an internal symmetry, but we don't know, we'll see. And in fact, any input that any of you have on something like this would be valuable.
Sorry, do you mean the non-compact finite dimensional Lie group?
Yeah, sorry, that's right. Yeah.
And so aren't your excitations, if it's a symmetry, your excitations should be in a unitary representation?
Yeah, that's correct.
But those would be infinite dimensional?
Yeah, I guess so. I guess that's correct. Yeah. So is that good or bad?
I'm not making a judgment, just an observation.
All right, very good. So I would like to be able to rule this out on some general ground or admit it if it's allowed, but we're not very sure whether this is allowed or not. So since we're not sure about that non-compact finite dimensional possibility, let me conclude by just talking about search Fermi liquids. So even if JAR and the anomaly are the same as in the Fermi liquid, the detailed universal dynamical properties can be completely different. We're only guaranteed the kinematic properties are the same. And in particular, in this case, there's an infinite dimensional continuous symmetry. So like in the Fermi liquid, there's infinite number of emergent conserved quantities. And this has tremendously strong implications for transport and other dynamical properties in such non-Fermi liquid metals. In fact, I think I've run out of time, so let me not really explain it, but it's based on thinking about the implications for transport and other things that we're able to make a concrete prediction for experiments in such Fermi liquids. So let me skip this unless someone really wants to hear and just go to the summary. I won't talk about experiments at all. And just summarize to say that the assumptions that we've made, which are well motivated in condensed matter physics, so global U1, lattice translation, and a tunable filling, lead to very strong constraints in the IR theory that must be satisfied by any putative non-Fermi liquid with these symmetries. And such Fermi liquids with infinite dimensional emergent symmetry are certainly possible. And if they are realized, they are what's going on in the experiments, then that gives us a way to start making statements about experiments in the absence of a detailed theory. But we don't know that they are the only possibility. And the real question is, how far can we go without committing to any particular detailed dynamical model? All right, let me stop here. Thank you.